Next, I am going to discuss the horizontal projection in projectiles. This horizontal projection can be considered as a special case of oblique projection from certain height above the ground. So first I am going to discuss the theory part of the horizontal projection. So when I am explaining the theory part, better you don't write any notes, don't try to write running notes while I am explaining. You just concentrate on listening. So after the discussion of the theory part, I will be showing you the notes, that I have printed notes in PowerPoint presentation. Then those who are interested to write the notes, they can write the notes later when I tell you to write the notes. But at present you concentrate just on listening to my discussion. So I am going to discuss about the horizontal projection. Earlier in the theory of oblique projection, the angle of projection of the projectile denoted by theta. That is the angle which the initial velocity makes with the horizontal direction, denoted by theta. The horizontal component of initial velocity, denoted by ux. The vertical component of initial velocity, denoted by ui. We have written ux equal to u cos theta, ui equal to u sin theta. So if theta is decreased, then for given value of u, if theta is decreased, magnitude of this horizontal component will increase and magnitude of vertical component will decrease. So when the body is projected horizontally from certain height above the ground, then we call it as a horizontal projection. So in this case, the angle theta which the initial velocity makes with the horizontal direction can be taken as 0 degrees. Therefore, vertical component of initial velocity uy will be u sin theta 0 degrees, that is equal to 0. The basic principle of the projectile motion is same both in the case of horizontal projection and oblique projection. So both in the case of horizontal projection and even in the case of oblique projection, the acceleration of the projectile is equal to the acceleration due to gravity, which acts vertically downwards. So the component of this acceleration in the horizontal direction is 0. So horizontal component of accelerated projectile will be 0. Therefore, the horizontal component of velocity of the projectile remains constant. So when theta is 0 degrees, u cos theta becomes u cos 0 degrees, or that is equal to u. That means the horizontal component of velocity of projectile during the motion under influence of gravity, in the case of horizontal projection, is same as the initial velocity of projection. And vertical component of initial velocity is 0. That means initial velocity in the vertical direction is 0. Here y is the point of projection. That means y is the point from where the body is projected horizontally. Let h be the initial vertical height of the point y above the level ground. Let a be the point on the level ground which lies directly below the point of projection. B the point on the level ground at which it strikes the ground. Let P denote the Position of the projectile at time t after projection. At which the velocity v bar makes some angle alpha with the horizontal direction. This velocity v bar can resolve into rectangular components along the horizontal and vertical directions. The horizontal component velocity at the point P is denoted by Vx. The vertical component velocity at the point P is denoted by Vy. The vertical distance through which the body falls in time t after projection below the initial position was denoted by letter Y. The distance covered in the horizontal direction at the same time t is denoted by letter X. So here also projectile motion can be considered as a combination of two mutually perpendicular motions. The motion in the horizontal direction is similar to the motion of body moving with constant velocity equal to u. The equations of motion for vertical direction will be similar to the equations of motion for a freely falling body. In the vertical direction, initial velocity is 0. The acceleration in the vertical direction is equal to the acceleration due to gravity which acts vertically downwards. The displacement y in the vertical direction also acts vertically downwards. Vy represents vertical component velocity at the point P, which is also directed vertically downwards. So that means in vertical direction, displacement y, in vertical velocity Vy, and acceleration, all the three are directed vertically downwards in the same direction. Therefore, you can give positive sign for all the three quantities when all the three quantities are directed in the same direction. That means vertically downward direction is taken as positive direction of axis, and horizontal direction as positive direction passing through the point O towards right as positive x-axis. So the accelerated projectile is equal to the acceleration due to gravity which acts vertically downwards. Its component in the horizontal direction is 0. So for motion in the horizontal direction, the horizontal component of acceleration is 0 and horizontal component of velocity remains constant throughout the motion under influence of gravity. And horizontal component of velocity is same as the initial velocity of projection. That means horizontal component velocity at the point P will be same as the horizontal velocity at O. The horizontal component velocity at the point P has magnitude V cos alpha. That can be written as equal to U. This I call equation number 1. I am numbering those equations which you need to remember. Displacement in the horizontal direction is covered with a constant velocity of magnitude U. Therefore, displacement x in the horizontal direction. In time t in oblique projection, we write x equal to u cos theta into t. But here theta is 0 degrees, so cos theta will be 1. So you can write x equal to u into t. So for motion in the vertical direction, the initial velocity is equal to uy. That can be taken as 0. And acceleration in the vertical direction are denoted by ay. that is equal to g. So acceleration is a constant in the vertical direction, which is equal to acceleration due to gravity. So if the height h from where the body is projected is negligibly small compared to the radius of the earth, then the acceleration of the projectile can be assumed to be constant throughout the motion under influence of gravity. So we can apply the equations of motion with uniform acceleration for vertical direction. So the equations of motion, if you use the formula V equal to U plus AT for vertical direction, can write Vy equal to Uy plus Ay into T. The initial velocity in the vertical direction is 0, acceleration in the vertical direction is equal to g. Therefore, vertical component of velocity time t after projection is given by Vy equal to gt. And if you use the equation S equal to ut plus half AD square next for vertical direction, you can write displacement y in the vertical direction in time t after projection Uy into t plus half Ay into t square. So if you substitute Uy equal to 0 and Ay equal to g, you get y equal to half gt square. This is called equation number 4. And if you use the equation v square 1 square equal to as for motion in the vertical direction, can write Vy square minus Uy square equal to 2Ay into y. To substitute Uy equal to 0 and Ay equal to g. So you can write Vy square is equal to 2gy. By comparison, you can observe that the equations of motion in the vertical direction look similar to the equations of motion for a freely falling body. For a freely falling body, we write V equal to gt, S equal to half gt square, and V square equal to 2gs. The similar way here, for motion in the vertical direction, we write Vy equal to gt, y equal to half gt square, and Vy square equal to 2gy. Next here, the velocity of the projectile at any instant. The velocity v bar of the projectile at a point P in its path makes some angle alpha with the horizontal direction. This velocity v bar at the point P in its path, as I discussed previously, can be resolved into two rectangular components along the horizontal and vertical directions. The horizontal component velocity should be denoted by Vx and vertical component velocity by Vy. So in rectangle, opposite sides are equal, so this side will be also equal to Vy. So we have a right angle triangle in the figure with one angle equal to alpha. The length of the side adjacent to alpha equal to Vx. Length of the side opposite to alpha equal to Vy. Length of the hypotenuse side equal to V bar. So V square we can write applying whether it's V square equal to Vx square plus Vy square, or magnitude of velocity at any instant is given by V equal to root of Vx square plus Vy square. So the horizontal velocity of the projectile in the case of horizontal projection, same as initial velocity projection. And vertical component velocity at time t after projection is given by Vy equal to gt. So magnitude of velocity at time t after projection can be written as root of u square plus g square t square. You can also write in another way. You can substitute Vy square equal to 2gy. In case you know the displacement in the vertical direction in the given problem at a particular instant, we can write v equal to root of u square plus 2gy. So coming to the method to find direction of the velocity, that is method to find the angle alpha. So if alpha is the angle with the velocity v bar makes with the horizontal direction at time t after projection, then tan alpha you can write Vy by Vx. And vertical component velocity at time t after projection is given by Vy equal to gt. And horizontal component velocity of projectile at any instant during the motion under gravity, same as the initial velocity of projection. So from this equation, you can find the direction of the velocity. This we call equation 6 and this as 7. Next, I would like to discuss about the equation of the trajectory of the projectile in the case of horizontal projection. Don't try to write the notes immediately now. For those who are interested to write the notes, they can write the notes separately. I will be showing you the notes on the screen in the PowerPoint presentation after complete discussion of the theory part. So displacement equation of trajectory is the relation between x and y in terms of constants. Displacement in the horizontal direction in time t after projection is given by x equal to u into t. From this equation, you can write t equal to x by u. Displacement in the vertical direction in time t after projection is given by y equal to half gt square. You can substitute t equal to x by u. So the equation of the trajectory in the case of horizontal projection is given by y equal to gx square by 2u square. You can get the same equation in magnitude if you substitute theta equal to 0 degrees in the equation of the trajectory which I have discussed earlier in oblique projection. So this equation is in the form y equal to kx square, where k equal to g by 2u square. The value of k is a constant for a given projectile which does not vary during the motion under gravity. So y proportional to x square. The relation y proportional to x square represents the equation of a parabola. So when in the case of horizontal projection, the path followed by the projectile is a parabola. So next in the case of oblique projection, I would like to discuss how to calculate the time of descent, means time taken by the projectile to reach the ground. As I explained earlier, where is the point of projection here? From where the body is thrown horizontally with initial velocity u. A is the point on the ground which lies directly below the point of projection. B is the position of the projectile at the instant when it strikes the ground. H represents the initial vertical height above the point of projection. That capital T denotes the time taken to reach the ground. So from this equation I have discussed previously, from the equation number 3, the displacement y in the vertical direction time t after projection is given by y equal to half gt square. Suppose if capital T represents the time taken to reach the ground, then we can say that small t equal to capital T, y equal to h. So we can write h equal to half g into capital T square. Or from same equation you can write to h by g equal to t square, or t equal to root of 2h by g. That means the time taken by the body to reach the ground when it is thrown horizontally from certain height h above the ground is given by capital T equal to root of 2h by g, which is independent of initial velocity of projection. You can observe that if there are two bodies, one is dropped from the point O so that it falls freely under gravity, and second one is projected horizontally from the point O with initial velocity u, then both the bodies take same time to reach the ground, given by T equal to root of 2h by g. That means in the case of horizontal projection, the time taken by the body to reach the ground, same as the time taken by another body that falls freely under gravity from same vertical height above the ground. Let R denote the total horizontal distance covered by the body when it reaches the ground. We call horizontal range of the projectile. So in the case of horizontal projection, the displacement x in the horizontal direction is covered with a constant velocity of magnitude u. So you can write x equal to r at small t equal to capital T. That means the total horizontal distance covered, that is the horizontal distance between the points A and B, we call horizontal range. That can be written as horizontal velocity to time taken to reach the ground, and time taken to reach the ground is given by root of 2h by g. Next here, would like to show you the PowerPoint presentation of the discussion I have done so far. I would like to summarize my discussion. I want to revise the entire discussion I have done about horizontal projection, so that those who are interested to write the notes, they can write the notes. So those who want to write the notes, they can get ready with the pen and notebook. So I am going to summarize the discussion I have already done, and also going to revise the discussion. For those who want to write the note, they can start writing the notes. So this is the diagram for horizontal projection. Where is the point of projection? So you can see the diagram, the same thing which I discussed earlier. Consider a body projected horizontally with initial velocity u bar from vertical height h above level ground. So P is the point which represents the position of the projected time t after projection. V bar is the velocity at P, which makes an angle alpha with the horizontal direction. Vx and represent the horizontal component velocity at P. Vy is the vertical component velocity at P. X is the horizontal displacement covered in time t after projection before it reaches the point P. Y is the vertical distance covered below the initial position O in the same time t. H is the initial vertical height above the level ground from where it is thrown horizontally. Point A is the point on the ground which lies directly below the point of projection, and B the point at which it strikes the ground, and R is the horizontal range. So if you want to copy the diagram also, you can copy down. Those who want to copy the notes, if they require, in case they require more time, they can take a pause and write the notes. The horizontal component of velocity in instant during the motion under gravity, same as the initial velocity of projection. For motion in the horizontal direction, Ax is 0. That means horizontal component of acceleration is 0. And Vx is constant equal to u. And magnitude of horizontal component velocity at P is same as the horizontal component velocity at O. That means V cos alpha equal to u. So those who want to write the notes, they can take a pause and copy the notes. Alpha is the angle which velocity V bar makes with the horizontal direction at a point P in its path. Horizontal displacement can be written as horizontal velocity in time interval, because the horizontal component of acceleration is 0. Displacement in the horizontal direction is covered with a constant velocity of magnitude u. So you can write x equal to u into t. That you call equation number 2. So those who want to copy the notes, they can copy the notes. In case you need more time to copy the notes, you can take a pause and copy the notes. For motion in the vertical direction, you can take initial velocity uy equal to 0 and acceleration ay equal to g. The equations of motion, I mean for vertical direction. First equation of motion, we can write Vy equal to Uy plus Ay into t. That means using the equation V equal to U plus At for vertical direction. You get Vy equal to Gt. That means we have substituted Uy equal to 0 and Ay equal to G. And if we use the equation S equal to At plus half At square for vertical direction, you can write Y equal to Uy into T plus half Ay into T square. You can substitute Uy equal to 0 and Ay equal to G. So you get Y equal to half Gt square. That you call equation number 4. If you use the equation V square minus square equal to As for vertical direction, you can write Vy square minus Uy square equal to Ay into Y. You can put Uy equal to 0 and Ay equal to G here. So you get Vy square equal to Gy. You can call it as equation number 5. So those who want to copy the notes, they can copy the notes. In case you need more time to copy the notes, you can take a pause and copy the notes. Magnitude of velocity in instant is given by V equal to root of Vx square plus Vy square. You can substitute Vx equal to U and Vy equal to Gt. So magnitude of velocity at time t after projection, you can write V equal to root of U square plus G square T square, which you can also write root of U square plus 2Gy. That means you can substitute Vy square equal to 2Gy from equation number 5. So those who want to copy the notes, they can copy the notes. In case you need more time, take a pause and copy the notes. Coming to find the method to find direction of velocity that discussed previously. For alpha is the angle which the velocity makes with the horizontal direction at time t after projection. Then tan alpha you can write Vy by Vx. And Vy can be written as Gt and Vx equal to U. So tan alpha can be written as Gt by U. We call it as equation number 7. Next equation of the trajectory of the projectile in the case of horizontal projection. For horizontal displacement, for horizontal motion, you can write x equal to U into T or T equal to x by U. Vertical displacement time t after projection is given by Y equal to half Gt square. We substitute T equal to x by U. You get Y equal to Gx square by 2U square, which you can write it as I equal to half Kx square, where K is a constant. So if you want to copy down, you can copy down the notes. You can take a pause if you need more time to copy the notes. K equal G by 2U square, therefore Y proportional to X square. Equation number 8, that means the previous equation number 8 represents the equation of a parabola. You want to copy down, you can copy down. Time of descent, that means time taken to reach the ground. If capital T is the time taken to reach the ground, then you can write y equal to h at small t equal to capital T. Using the equation number 4, where vertical displacement is given by y equal to half gt square. You can put y equal to h at small t equal to capital T. So you can write small h equal to half g into capital T square. From this equation, 2h by g equal to t square, or t equal root of 2h by 9, that you can call it as equation number 9. T equal root of 2h by g, which you can call it as equation number 9. So those who want to copy the notes, you can copy the notes. In case you need more time to copy the notes, you can take a pause. So the conclusion here you have to remember is that the time taken by the body to reach the ground is the same as the time taken by another body which falls freely under gravity from the same height. Calculate the range. The horizontal distance covered by the body when the body reaches the ground, a range is given by r equal to u into capital T. Can write here capital T equal to root of 2h by g. So horizontal range or horizontal distance covered in the case of horizontal projection when it reaches the ground is given by r equal to u into root of 2h by g. Next I am going to discuss one special case. So I am going to discuss a special case in horizontal projection. You can just listen now, stop writing and listen. I will again show you the notes for this special case separately after my discussion. You find some questions based on this special case in different books. Let us consider two bodies which are projected horizontally in opposite directions from same point. From a vertical height h above the ground. That means one body is projected horizontally with initial speed u1. Second body is projected horizontally with initial speed u2 in opposite directions from same position, that is from the top of a tower. Sometimes you may be asked to find the time after projection at which velocity of one projectile is perpendicular to the velocity of other projectile. I am going to discuss a calculation for that. So if you want to choose, we can coordinate axis, we can choose the direction of the initial velocity of one of the projectiles as x-axis and vertically downward direction as y-axis. The point of projection as origin, that is vertically downward direction, we take it as positive axis. So velocity of projectile at time t after projection. In the case of horizontal projection, if you want to write in vector form, you can write as v bar equal to I cap into Vx plus j cap into Vy. The horizontal velocity of projectile in the case of horizontal projection same as the initial velocity of projection. The vertical component velocity at time t after projection is given by Vy equal to gt. So here the initial velocity of first projectile is in the positive x direction, then initial velocity of second projectile is in the negative x direction. Let V1 bar denote the velocity of the first projectile at some instant of time t after projection, and V2 bar represent the velocity of second projectile at the same instant. We want to find the time after which V1 bar is perpendicular to V2 bar. So let us suppose that the instant of time t equal to t1, V1 bar is perpendicular to V2 bar. So using the earlier equation, V1 bar you can write, U can be taken as U1 for first body, projectile. T equal to T1, at the instant T equal to T1. For second projectile, initial velocity is opposite to U1. That means U2 bar, U2 depends on the initial speed of projection second projectile, which is directed toward left side. So for second projectile, Vx can be taken as minus U2. Because it is directed towards left side in the negative direction of x-axis. But Vy equal to Gt. So at T equal to T1, Vy equal to Gt1. Want to find the time after projection at which the velocity of one projectile is perpendicular to the velocity of other projectile. V1 bar is perpendicular to V2 bar. So let us suppose at the instant T equal to T1, V1 bar is perpendicular to V2 bar. As you studied in vectors, probably, of course in multiplication of vectors, that if two vectors are perpendicular, then the dot product of the two vectors will be 0. So at the instant of time T equal to T1, V1 bar is perpendicular to V2 bar, means V1 bar dot V2 bar will be 0. So if you take the dot product of these two vectors, in general as you studied in vectors, if A bar and B bar are two vectors which lie in the xy plane, then A bar dot B bar you can write AX BX plus AY BY. So here V1 bar dot V2 bar can be written as U1 into minus U2 plus GT into GT1 into GT1. That is 0. So you get GT1 whole square equal to U1 U2. Or you can write GT1 equal to root of U1 U2. So the time after projection at which velocity vector of one projectile is perpendicular to the velocity of a vector of other projectile is given by T1 equal root of U1 U2 by G. Don't start writing the notes now. I will show you the notes for this separately. Those who are interested to write the notes, they can write the notes later. The same way, sometimes you may be asked to find the time after projection at which the position vector of one projectile is perpendicular to the position vector of the other projectile. Let R, the position vector of the projectile with respect to the point O, that is point of projection as origin, denoted by R bar, can be written I cap into X plus J cap into Y. The displacement X in time T after projection, you can write U into T. The displacement Y in vertical direction time T can be written as half GT square. So position vector of one first projectile, you can write R1 bar equal to U1 into T into I cap plus J cap into half GT square. But displacement X in the horizontal direction for one projectile is directed towards right. The displacement in the horizontal direction for the other projectile is directed towards left side. That means if horizontal displacement of the first projectile is along parallel to positive x-axis, then the horizontal displacement of second projectile is parallel to negative x-axis. Therefore, R2 bar for second projectile you can take U equal to minus U2 because X is coordinate of second projectile is directed toward left side. So for second projectile, you can write x equal to minus u2 into t. But y is same for both. You can write half gt square. So we want to find the time after projection at which r1 bar is perpendicular to r2 bar. So the position vector of the two bodies are projected horizontally in opposite directions. In the special case which I was discussing. So r1 bar is the position vector of one of the projectiles, time t after projection. So r2 bar is the position vector of other projectile at the same instant of time. We want to find the time after which r1 bar is perpendicular to r2 bar. So let us suppose that the instant of time t equal to t2, r1 bar is perpendicular to r2 bar. So r1 bar you can write xi cap, x equal to u1 into time, that is t2, plus yj cap, y equal to half gt square. You can write t equal to t2 there. R2 bar you can write at the same instant of time, x into I cap, x equal to minus u2 into t, or t equal to t2, plus yj cap, y equal to half gt square. You can put t equal to t2 here. So at the instant of time t equal to t2, r1 bar is perpendicular to r2 bar. When two vectors are perpendicular, dot product of the two vectors becomes 0. So r1 bar dot r2 bar becomes 0. So dot product of two vectors a bar and b bar which lie in the xy plane is given by ax bx plus ay by. That means you have to take the product of x components first. That is u1 t2 into minus u2 t2 plus next product of the y components, half gt2 square multiplied by half gt2 square. That is equal to 0. So you get half gt2 square whole square equal to u1 u2 into t2 square. So take positive root both sides because time cannot be negative. Half gt2 square equal to t2 into root of u1 u2, or you get t2 square by t2, 2 root of u1 u2 by g. So the time after projection at which the position vector of one projectile is perpendicular to the position vector of other projectile is given by t2 equal to 2 into root of u1 u2 by g. So I would like to show you the notes for the same special case which I am going to show now. The notes for the same special case, that is PowerPoint presentation. So for those students who want to make the notes, write the notes, they can next copy the notes when I show the printed notes for same special case. So next I am showing the notes for the same special case, that is the PowerPoint presentation. Those who want to copy the notes, they can copy the notes now. I once read out the conclusion which I just discussed before. Consider two bodies projected simultaneously from the top of a tower horizontally in opposite directions with initial speeds u1 and u2 at t equal to 0. The time after projection at which their velocity vectors are perpendicular to each other is given by t equal to root of u1 u2 by g. So if you want to copy the notes, please copy down the notes. In case you need more time to write the notes, you can take a pause wherever required. The second conclusion in the same special case, the time after projection at which the position vectors of the two bodies with respect to initial position as origin are perpendicular to each other is given by T2 equal 2 into root of U1 U2 by G. Or you can write T2 equal to T1. Come on, copy down the notes. Now I have first shown you the conclusions directly. Next I am going to show you the calculation part for these conclusions which I explained previously. Calculation for first result. You can write V bar equal to Vx I cap plus Vy j cap. You can write Vx equal to U and Vy equal to Gt there. For two bodies at the instant of time t equal T1. V1 bar you can write U1 I cap, U equal to U1 for first body and U equal to minus U2 for second body. At T equal to T1, Vy equal to Gt1 for each body. So at T equal to T1, V1 bar dot V2 bar is 0 when they are perpendicular. So the dot product V1 bar dot V2 bar you can write minus U1 into minus U2 plus Gt1 into Gt1 or means Gt1 whole square. So you get Gt1 whole square equal to U1 U2 or Gt1 equal to root of U1 U2 or T1 equal to root of U1 U2 by G. This is the calculation for first result. So those students who are copying the notes, please copy the notes. In case you need more time to copy the notes, you can take a pause and copy the notes. I would like to show the calculation for second result. This is the calculation for second result. First result I have already shown, that again I am showing here. For second result, we can write position vector r bar at time t after projection is given by cap into x plus j cap into y. You can write x equal to ut in the case of horizontal projection, y equal to half gt square. For two bodies at the instant t equal to t2. For the first body, you can write position vector as r1 bar and u equal to u1 and t equal to t2 at the instant t equal to t2. For second body, you can write u equal to minus u2 and t equal to t2 at the instant t equal to t2. So at t equal to t2, r1 bar dot r2 bar becomes 0 because they are perpendicular to each other. So if you take the dot product r1 bar dot r2 bar, you get product of x components as minus u1 u2 into t2 square. Product of the y components is half gt2 square whole square. That the dot product r1 bar dot r2 bar becomes 0 at t equal to t2. So those who want to copy the notes, please copy the notes. In case you need more time to copy the notes, you can take a pause and copy the notes. We simplify the last equation further. You get half gt2 square whole square equal to u1 u2 into t2 square or half gt2 square. If you take positive root both sides, t2 into root of u1 u2, or you get t2 square by t2 equal to 2 root u1 u2 by g, or t2 equal to 2 into root of u1 u2 by g, or you can say t2 is 2t1. So those who want to copy the notes, please copy down the notes. In case you need more time to copy the notes, you can take a pause and copy the notes. So in next class, I will be showing you some questions in the assignment in projectile. That means I will continue the assignment in projectile from question number 41 onwards, where most of the questions will be based on horizontal projection.